There are galaxies in the night sky that challenge everything we think we know. Ancient light, crossing billions of years, carrying secrets from a universe too young to understand them. Some of these galaxies spin faster than gravity should allow. Some shine brighter than physics predicts. Some are too massive, too organized, too complete, far too early in time. They are galaxies that should not exist, and yet, quietly, magnificently, they do. If this calm journey brings you even a moment of wonder or peace, I'm deeply grateful you're here. Your gentle like or a soft tap on subscribe helps me continue creating these quiet voyages through the cosmos. Thank you for being part of this slow, starlit exploration. Now, let's drift into the first truth. Part 1. The universe wasn't supposed to build so fast. In the earliest chapters of the cosmos, gravity was still learning to sculpt. Matter was scattered, chaotic, expanding rapidly into a cold and silent vacuum. Yet, telescopes like James Webb keep finding mature, massive galaxies, already thriving just 300 million years after the Big Bang, long before theory says such structures could form. It is as if the universe rushed ahead, skipping steps in its own story. To understand this mystery, imagine the universe as a newborn world still catching its breath. Everything was hot and dense, a smooth sea of particles drifting apart. For a long time, there were no stars, no clusters, no cosmic structure. We call this era the Dark Ages, a time when the universe was too young to shine. According to the rules written in our physics textbooks, order should take patience. Gravity must gather invisible dark matter first, stacking it into scaffolds strong enough to anchor gas and dust. Only then can stars ignite. Only then can galaxies assemble. And yet, when astronomers aim their most powerful eyes toward the deep past, toward light older than our planet, older than the sun, they find something astonishing. Galaxies already exist in abundance, bright, enormous, shockingly mature. The James Webb Space Telescope has revealed systems that seem to have skipped entire evolutionary stages, appearing as well-formed families of stars when the universe was only a few percent of its current age. It's like walking into a hospital nursery and discovering children who are already grown. Even as your body rests now, drifting through the dark comfort of night, those galaxies continue shining across a gulf of time so vast that their photons began their journey billions of years before life emerged on Earth. They are messengers of a truth we do not yet fully understand. Scientists expected the early universe to look primitive, a scattered collection of small, forming clumps just beginning their slow dance into gravity's embrace. Instead, the data shows galaxies that are far more massive than any model predicts. Some seem to hold 10 times more stars than they should be able to form, so soon. These giants defy expectations, like cities appearing before villages, skyscrapers rising before huts. It raises a quiet but profound question. Did the universe find a faster way to build than we have imagined? As we look deeper into this puzzle, we see more than size alone. These ancient galaxies are organized, shaped, structured. Some are already forming spiral arms, delicate patterns of rotation that usually emerge only after billions of years of slow gravitational choreography. Spiral galaxies, in theory, need time, lots of it, to settle into graceful order. Yet, they are there, already spinning, already beautiful. Gravity, a force that works with silence and patience, seems to have hurried. One explanation suggests that dark matter, that invisible substance forming the hidden backbone of every galaxy, may have been denser, more efficient at gathering material in the beginning. If dark matter collapsed faster than expected, it could have helped galaxies grow, with surprising speed. In this scenario, the universe was not chaotic but eager, bending its own laws toward creation. Another idea whispers something even stranger. Perhaps the physics of the early cosmos was not the physics we know today. The conditions right after the Big Bang were extreme, temperatures and energies beyond anything we can recreate. Under such intensity, the laws that govern matter may have behaved differently. Gravity might have been stronger, cooling might have been faster, star formation may have ignited like wildfire. If that's true, The universe remembers an ancient rule that we have not yet rediscovered. And as we listen to the cosmos, we realize how little we truly know. Even the stars themselves challenge our expectations. Many early galaxies contain elements, carbon, oxygen, heavy metals forged in supernovae, suggesting that several generations of stars must have lived and died before we observed them. But there simply shouldn't have been enough. Time for that cycle to have already occurred. The universe was rushing, not gradually building, but leaping. Astronomers call this era cosmic dawn, the moment when the first starlight pierced the darkness. We imagine those first stars as rare and lonely. Now it appears they burst into existence in great numbers, lighting the universe far faster than expected. As you breathe slowly, feel the calm of this revelation. The universe you rest within is more capable, more efficient, more confident than the equations we write about it. But these discoveries do not erase the darkness that came before. They make it all the more mysterious. What happened in that silent gap after the Big Bang? What forces shaped the first gravitational seeds? How did structure bloom from chaos so quickly? Some researchers suspect that our cosmic timeline might need adjusting, that our interpretation of distance and age could shift as we understand the early universe's expansion more precisely, because every observation we make of those ancient galaxies is a glimpse through bent and stretching space-time. It is a view through a lens shaped by gravity itself. Time in the young universe may not have flowed as smoothly as it does now. The more we look, the more the early cosmos seems like a place where nature was not testing ideas but perfecting them. A universe not hesitating, but already knowing what it wanted to become. Vast clusters, spirals of stars, black holes already growing into giants. It is humbling to realize that the universe did not wait for us to understand its pacing. These galaxies existed billions of years before Earth formed, before the first ocean rippled with life, before the first cell divided in silent darkness. And tonight, their ancient photons brush gently against your eyes, your walls, your window, a fragile echo from a time when the cosmos was still learning how to shine. As we continue this quiet journey through impossible galaxies, one question glows softly beneath them all. What force helped the universe build so fast? And why do those earliest creations seem so complete? Because if the beginning of time was more powerful, more organized, more determined than we believed, then the story of everything is richer and more mysterious than any model has dared to predict. And as the universe keeps unveiling these early giants, another deeper mystery emerges. A question about what lies at their hearts and whether the most massive galaxies were guided by an invisible architect. Now, let us drift into the next truth. Part 2. Giants Too Early, the Overgrown Galaxies. Some galaxies in the early universe contain more stars than entire modern galaxy clusters. They are impossibly huge, their mass assembled too quickly, as though gravity worked overtime. Astronomers call them massive high redshift galaxies, evidence that the cosmos may have been building giants while still in its infancy. These early giants defy the natural timing of growth. They stand as cosmic contradictions, galaxies so large and so bright that they seem to leap ahead in the evolutionary script. When astronomers detect them, the first reaction is often disbelief. Instruments are checked, measurements double-checked, models recalculated, yet even after every cautious step, these galaxies remain too massive, too organized, too soon. To fully appreciate why they are so puzzling, imagine the universe just beginning to form structure. Gravity is only beginning its slow work of gathering hydrogen gas into clumps. Those clumps collapse into the first stars, enormous and unstable, burning out in just a few million years. After a supernova explosion enriches the surrounding gas with heavier elements, new generations of stars follow. This process, repeated countless times, fills galaxies with starlight, but only after billions of years. Or at least, that's the story we believed. But when we observe the universe as it appeared 500 million years after the Big Bang, we find galaxies tens or even hundreds of billions of times more massive than our sun. Mature populations of stars shine within them, Not just young, blue stars born moments earlier, but older, metal-rich stars that should not exist yet. Those stars require several cycles of life and death to form their elements. There should not have been enough time. Yet the light we see proves they are there. Even as you lie still, breathing gently, your body is surrounded by this ancient radiation, traveling unimaginable distances to reach us, carrying a message that the early universe was a far more ambitious architect than we ever guessed. Some of these galaxies contain more stars than the Milky Way does today, and the Milky Way has had nearly 14 billion years to build its grandeur. These early titans may already have held several hundred billion stars when the cosmos was in its first faint dawn. They did not slowly gather dust and gas. Their growth appears explosive, as though star formation ignited at a pace far beyond what physics predicts. One idea is that these giants formed from extraordinarily dense regions of dark matter, places where the invisible structure of the universe collapsed early and quickly. Like a deep valley collecting water, these gravitational wells could have sucked immense amounts of gas into a single region of space. Stars would then ignite in a frenzy, a cosmic starburst filling the galaxy with brilliant light. But even this explanation strains our models. The sheer mass of these galaxies suggests dark matter halos too large to have formed so soon. It would be like discovering mountains rising instantly from a flat plain, geological time crumpled into an impossible speed. Another puzzle emerges when we consider the chemistry of these galaxies. Heavy elements, everything from carbon in your breath to iron in your blood, are forged in stars. They require time. Yet these early giants contain surprising amounts of these elements. This means multiple generations of stars must have lived and died before their light reached us. Generations, in a universe that had barely begun. Everywhere we look in these galaxies, we find signs of hurry. And there's another quiet truth buried inside their structure. Many of these systems already show the signs of central supermassive black holes. Such black holes require immense amounts of gas to feed on. They grow slowly, over billions of years of swallowing stars and dust. Yet, in these ancient times, the black holes seem already enormous, already shaping their host galaxies with powerful gravitational influence. It is as if both the galaxies and the black holes at their centers took a shortcut together, rising to maturity without passing through childhood. Astronomers had long believed early galaxies must be small and chaotic, colliding often as they slowly assembled into larger shapes. But these giants look remarkably calm. Their stars are arranged into tight disks or smooth ellipses. Their light appears steady, not flickering in violent bursts. This tranquility suggests they formed efficiently, not through endless collisions, but through rapid, orderly growth. The universe, in its earliest days, was supposed to be rough, a place of clumps and chaos. Yet these galaxies look civilized. Every message we receive from them challenges our assumptions, like a student who masters a subject before the teacher has even begun the lesson. So what could explain such haste? Perhaps gas was more abundant, falling into galaxies at rates far higher than any simulation has predicted. Perhaps star formation was far more efficient, with little waste and little time between birth and ignition. Perhaps feedback mechanisms, the cosmic braking systems that normally slow down star formation, were weaker or absent. Or perhaps something far more profound is at work. Maybe our understanding of time in the early universe is incomplete. The expansion of space, the cooling of matter, the formation of structure, these processes may have flowed differently when everything was young. The universe may have been more agile, freer to build quickly, unconstrained by the inertia of age. Some scientists have even wondered whether new physics is required, an adjustment to gravity itself, or a deeper insight into dark matter's behavior. Because if the universe created giants in its first moments, then the rules we rely on may only describe the world after it slowed down. Tonight, these early galaxies become more than scientific curiosities. They become symbols of possibility, proof that creation can exceed expectation. They remind us that the universe has never needed permission to be greater than our equations. It simply evolves quietly and endlessly, surprising those who study it. As you drift deeper into rest, let yourself feel the enormity of this discovery. The universe did not grow timidly. It did not wait. It built wonders at impossible speed. Each impossible galaxy carries a silent question, an invitation to rethink everything we know. And each new observation draws us toward the next layer of mystery, toward the engines that powered this ancient abundance. Because behind every overgrown galaxy lies an even deeper secret, a question pulsing at their centers. What fueled their rapid shining growth, and what invisible structures held them together so young? Now, we gently turn the page and wander into the next truth. Part 3. Spirals that shouldn't be spinning. Yet graceful spiral arms require time, billions of years of rotation, collision, and calm, and yet JWST has found elegant spirals already unfurling when the universe was barely a toddler. Their existence whispers a contradiction. Order emerged long before chaos had time to settle. A spiral galaxy is not simply a cluster of stars, it is a masterpiece of structure. Each arm is a flowing river of light, a pattern carved by gravity and motion, stretching across tens of thousands of light years. In the modern universe, spirals like the Milky Way are common, but they are the result of long, quiet evolution. Stars must have time to orbit the center repeatedly, tracing their gentle curves across cosmic history. Disks need patience to flatten. Gravitational disturbances, collisions, turbulence, and violent starbursts must calm before symmetry appears. But that calm wasn't supposed to exist in the beginning. When the first galaxies formed, the universe looked nothing like today. Matter was clumpy and uneven, gas clouds crashed together at immense speeds, baby galaxies collided frequently, merging into irregular shapes. The earliest formations should have been messy, distorted, and chaotic. In this era, spirals should have been impossible. And yet, through James Webb's deep infrared gaze, we find them. Arms neatly wrapped around bright cores, rotation already organized, young, disks already dancing. To see this while the universe was less than 1 billion years old is like finding a perfect seashell in a storm still raging across the ocean, improbable, delicate, and full of questions. As you take a slow breath, imagine time compressed. 1 billion years in the life of a galaxy is infancy, a blinking moment. And yet these spirals look like they've had eternity to grow. Why? One idea is that these early spirals formed from gas far more smoothly distributed than our models predicted. If clouds of hydrogen fell inward toward the center in a balanced flow, not in violent lumps, then disks could stabilize more quickly. Perhaps dark matter halos, the invisible frameworks that galaxies cling to, were unusually well-shaped, guiding gas into rotation with surprising precision. In this view, the early cosmos wasn't chaotic at all, it was efficient. Another possibility suggests that these spirals spun faster than we predicted. When a galaxy rotates quickly, centrifugal forces help create a disk-like structure sooner. But faster motion comes with consequences. If they spin too fast, they would fly apart. Something must have anchored them, holding stars in place despite their speed. That something is dark matter, but maybe more dark matter than we expected. Dark matter acts like a hidden conductor, shaping the dance of stars with silent gravity. If early spirals contained a heavy concentration of this invisible mass, they could form stable disks in far less time, neatly sculpting arms that wind outward like glowing ribbons. Still, even dark matter doesn't explain everything, because spiral arms are not static. They are patterns, like traffic jams that move along a highway even when the cars themselves change. These patterns require density waves, regions where gravity temporarily slows stars, bunching them into brighter streaks. For that to happen so early, galaxies had to reach a level of dynamical maturity that should have taken billions of rotations. They reached that calm state while the universe was still loud. Some astronomers wonder whether the first galaxies were born spinning, inheriting angular momentum from the swirling clouds that formed them. If the universe twisted slightly during inflation, that rapid expansion right after the Big Bang, then the first galaxies might have been imprinted with rotation from the start. In that case, spirals wouldn't be surprising. They would be a memory of the universe's first motion, a cosmic echo. But there is yet another intriguing layer to this mystery. Spiral arms depend on time, but the early universe may not have experienced time the way we do. Space was expanding more quickly. Gravity operated in denser regions. Gas cooled faster than once believed. If these processes unfolded at a different rhythm, a faster tempo, then the early universe might have reached certain milestones sooner, even though less time had actually passed. In other words, galactic growth may not follow a universal clock. As you rest, let that thought soften into perspective. The cosmos may not measure age the way we do. Stars do not count seconds. Galaxies do not heed calendars. They grow according to the rules written in gravity, not the rules printed in textbooks. Yet there's something especially poetic about early spiral galaxies. Their arms gently curve outward, as if reaching for a future they somehow sensed, a future where galaxies like ours would be common. But in their youth, they were pioneers, icons of organization in a universe still learning structure. Some of these spirals show bars lining their centers, straight lanes of stars that guide gas inward, feeding black holes and triggering star formation. Bars are not beginner features. They are hallmarks of advanced galactic evolution, and yet they appear shockingly early, as if the cosmos skipped ahead in architectural design. It raises a quiet question. Did galaxies evolve faster than we thought, or were they always meant for this symmetry? Even the colors of these spirals hint at maturity. Their stars are not just newborn blue suns, but include richer, older populations. Heavy elements, the ashes of earlier stars, glow in their light. That means cycles of birth and death had already repeated many times in their cores. Stars had lived, stars had died, stars had enriched the universe, all before spirals fully unfurled. The timeline bends. The more we observe these systems, the more they challenge our understanding. The early universe was not just creating structure, it was perfecting it. And while our minds expect disorder followed by gradual improvement, nature demonstrates the opposite. Sometimes beauty forms first and chaos follows later. Tonight, these spirals remind us that the universe is not obligated to match our expectations. It is not a student learning from our theories. It is the author of those theories, and we are simply discovering the chapters already written. As we continue traveling deeper into these ancient structures, another mystery comes into view. At the centers of many spirals, even the youngest ones, lurk black holes already millions or billions of times more massive than our sun. They may be the engines that helped organize these galaxies so soon, binding their stars together and shaping the calm we now witness. Which leads us gently to the next question in this quiet cosmic puzzle. How did the invisible matter and unseen forces in the early universe act so quickly? And what secrets do they still keep buried in the hearts of these unexpected spirals? Now, we drift softly toward the next truth. Part 4. The Dark Matter Puzzle. Dark matter should shape every galaxy, holding stars together like an invisible skeleton. But some early galaxies appear strangely compact, spinning faster than their mass allows. They behave as if cradled by a deeper gravitational force, or missing one entirely. In the calm night around you, every object you've ever known, your body, the earth, the moon, every star in the sky, is made of ordinary matter. The matter we can touch, the matter that forms planets and people and the familiar world. Yet, astonishingly, this visible matter makes up less than 5% of the universe. Everything else is hidden. Dark matter was discovered not by being seen, but by being felt. When astronomers measured how fast stars orbited their galaxies, they realized something was wrong. The outer stars were moving far too quickly, fast enough to fly off into the void, and yet they remained bound. Something unseen was holding them in place. That invisible glue became known as dark matter, transparent, silent, yet more massive than everything we can see combined. Modern galaxies fit this picture well. Their visible shapes rest inside vast halos of dark matter, like fireflies trapped in a glass sphere too large to notice. Gravity from the dark halo dictates how fast stars can move without escaping. In the present-day universe, the speeds and shapes all match. But in the earliest galaxies, the story seems to change. When we peer back nearly 13 billion years, we find galaxies that rotate faster than their visible mass can explain. They spin as though they contain far more dark matter than we can detect, or as though they rely on a gravitational law we do not yet understand. Some galaxies, incredibly, show the opposite problem. They appear to lack dark matter almost entirely. Their stars behave as if floating freely, unanchored by invisible mass. How can two opposite extremes exist in the same young universe? You can imagine the early cosmos as a construction site. Galaxies are being built quickly, messy scaffolding everywhere, dark matter forming the structural support. That support should be essential. Without it, the building collapses. Yet some buildings stand tall with no beams at all. To explain this contradiction, scientists have proposed several ideas. The first suggests that dark matter halos in the early universe were denser and more concentrated. If dark matter collapsed gravitationally faster than normal matter did, it could create tightly packed cores. Stars forming in these cores would orbit faster, staying bound by dark forces compressed into small volumes. These galaxies may look compact because they are deep wells of gravity, where dark matter is stacked more thickly than we ever expected. But then we see the galaxies with the opposite behavior. How could dark matter be missing? Did it dissipate? Did it fail to form properly? Or, more provocatively, were these galaxies never governed by dark matter in the first place? Some physicists wonder whether gravity itself behaves differently at extremely high densities or energies, especially in the early universe. If the laws of motion shift slightly under those conditions, galactic rotation could follow. Rules that don't match our current models. In this scenario, the universe didn't need dark matter yet, because gravity was working overtime on its own. A subtle change in the law of gravity would make stars orbit more tightly, just as if invisible mass were strengthening the pull. But that idea carries another consequence. If gravity evolved over time, then physics itself is not fixed. Other researchers explore interactions between dark matter and ordinary matter that could push dark matter outward or strip it away entirely under certain conditions. Maybe early galaxies formed so violently, through collisions and bursts of star formation, that dark matter was flung to the outskirts, leaving only the luminous core behind. This would create a deceptive picture. The stars would seem unsupported, but the dark matter would simply be farther out of sight. As you breathe slowly, think of how much we assume from shadows. Dark matter is not observed directly, it's inferred from motion. We draw the skeleton because of how the body moves. But in the earliest galaxies, the movement sometimes tells a different story, a skeletal frame that bends unexpectedly or vanishes altogether. There is another layer to consider. Dark matter is patient. It influences through gravity alone, and gravity is a slow artist. In the beginning, that process may not have reached full strength. Perhaps the structure of the dark universe was still growing, still stretching its web through cosmic space. In that early time, galaxies may not have been fully embedded into dark halos yet. They might have existed like drifting lights, guided by seeds of gravity not yet mature. We may be witnessing them mid-formation, catching the dark matter arriving late to its own design. The James Webb Space Telescope gives us only a snapshot, a frozen moment in a long transformation. It might be like witnessing a tree whose roots have not fully taken hold. The branches twist and sway strangely, not yet in balance. That imbalance doesn't break the laws of physics. It simply reflects how young the system is. Still, the anomalies cannot be ignored. Some early galaxies rotate so precisely that they suggest a well-formed gravitational structure. Others look wild and unstable, spinning in ways that imply missing mass. This inconsistency could mean that dark matter clumped unevenly, forming pockets of order inside widespread chaos. The cosmos may have taken creative liberty, building some galaxies with deep invisible foundations and others with temporary scaffolding that later collapsed or transformed. Dark matter itself remains elusive. It does not emit light, it does not absorb it. It does not collide with atoms. We detect it only through its pull. And if the universe behaved differently in its earliest moments, then the fingerprints of dark matter may appear distorted to us, like reflections wavering across rippling water. Tonight, as the sky above you turns in silence, consider how much of reality is unseen. The stars we admire are only the surface of a much deeper structure, a universe whose true architecture is hidden behind a veil of gravity. These early galaxies ask us a gentle, troubling question. What if we have misunderstood the universe's first blueprint? Did dark matter guide the youngest stars? Or did gravity follow a different rhythm then, a stronger beat that later slowed into the calm we now observe? This is why the dark matter puzzle is not just about hidden mass, it is a challenge to our understanding of the cosmos itself. As we move deeper into this mystery of impossible galaxies, another truth reveals itself, not about what holds them together, but about what fuels their brilliant growth. Because alongside these dark puzzles, the early universe burned fiercely with creation, lighting vast star factories that should not yet have existed. And so, gently, we drift toward the next question. How did galaxies produce so much light, so much energy, so quickly, in a universe that had only just woken from darkness? Now, let us continue into the next quiet revelation. Part 5. The Cosmic Dawn's Bright Beacons. Quasars, powered by supermassive black holes, blaze at the centers of galaxies. But finding them only a few 100 million years after the Big Bang raises a mystery. How did black holes grow into monsters so quickly? Their light suggests an engine more powerful than our models expect. A quasar is one of the brightest objects the universe can produce. To the human eye, it looks like a star, a single, sharp point of light. But behind that point is a titan, a black hole devouring matter so violently that the very space around it glows. Gas swirls inward at incredible speeds, heated to millions of degrees as it spirals into the gravitational abyss. That heat becomes light, radiant, intense, and strong enough to outshine entire galaxies. In the universe we know today, such enormous black holes sit at the hearts of mature galaxies like ours. The Milky Way's central black hole, Sagittarius A, contains the mass of 4 million suns. Other galaxies host even larger beasts, weighing billions of solar masses. They are ancient, grown slowly over cosmic lifetimes. But James Webb and other deep telescopes reveal something unexpected. Supermassive black holes already existed at the universe's beginning. Not small seeds, not quiet, newborn stars collapsing into compact hearts. No, these were monstrous giants, millions to billions of times more massive than the sun, appearing when the cosmos was still in its youth. It's like discovering towering redwoods just moments after the first saplings appear. Even as you rest now, imagine that early epoch, space still hot from its creation, stars just learning to shine. And yet, in that newborn universe, quasars ignited like cosmic lanterns, bright enough to pierce across 13 billion years of dark. Their brilliance tells us something profound. Those black holes must have grown at impossible speed. But how? Black holes typically gain mass slowly, feeding on gas, stars, and occasional collisions with other black holes. The process is not efficient. Much of the matter flings outward in blazing jets before ever crossing the event horizon. Physics imposes a limit on how fast a black hole can feed before the incoming light pushes matter away. This is known as the Eddington limit. And yet, the masses we observe in these young quasars exceed what is possible under those rules. It suggests something different happened there, something dramatic, something urgent. One idea is that the first black holes were born from truly colossal stars, giants far larger than anything alive today. These population 3 stars, forged from the pristine hydrogen of the early universe, may have lived briefly and died explosively, collapsing directly into black holes already tens of thousands of times more massive than our sun. If the first seeds were born enormous, maybe their rapid growth isn't so surprising. But many astronomers suspect something even more extraordinary, that the first black holes could have formed directly from collapsing gas clouds, skipping the star stage entirely. In this scenario, gravity grabs a huge cloud of primordial gas and crushes it inward so rapidly that it bypasses nuclear fusion. No starlight, no supernova, just immediate collapse into a black hole hundreds of thousands of solar masses strong, a head start beyond anything found later. Others explore a different possibility. Maybe the early universe fed black holes more efficiently than the present one. Gas fell in faster, thicker, without being blown away by radiation. Matter could plunge inward in great torrents, unchecked by the usual physical barriers. Black holes then might have feasted like never again in cosmic history. There's another idea, one that stirs even deeper questions. What if physics itself was different in that early epoch? Gravity might have acted more aggressively when the universe was still dense and compact. Space-time may have curved more easily, letting black holes gather mass at speeds we cannot reproduce. Or dark matter could have played a role, sinking into galaxies' centers and feeding black holes from within, silent and unseen. Because when we observe those quasars, they are not faint whispers. They are roaring engines, powerful enough to illuminate the universe in a time when much of it was still steeped in darkness. Astronomers call that period cosmic dawn, when the first stars, the first galaxies, and the first beams of light pushed back the ancient shadows of the Dark Ages. Quasars were like cosmic lighthouses, illuminating space not only with their brilliance, but also with clues about what existed around them. Their light, stretched across billions of years, reveals clouds of gas between us and them. It shows us when the universe first became transparent to starlight. It shows us the chemical fingerprints of early stars. It even reveals how galaxies clustered and grew around these central monsters. In a way, quasars are time capsules, preserving the history of the universe's awakening. But there is something almost contradictory about their existence. Black holes are symbols of destruction, gravity consuming everything near them. Yet in the beginning, they played a role in the birth of cosmic order. Their gravitational pull helped galaxies form, shaping the motion of stars, anchoring matter into structure. Creation and collapse intertwined. Tonight, as your thoughts drift quietly, imagine the stillness of space pierced by these brilliant beacons. Light crossing expanses you cannot fathom, photons traveling unbroken through time so long that entire planets formed and civilizations rose and fell while they moved steadily forward. A quasar shining in the first billion years is not merely a bright object, it is a defiant statement from the universe. I evolve faster than your equations allow. As scientists study these early black holes, they find diversity too. Some sit within enormous, rich galaxies, bursting with stars. Others appear lonelier, as though they grew first and their galaxies formed around them later. This confidence, this ability for structure to build from the center outward, challenges our understanding of the cosmic sequence. In our models, black holes are shaped by galaxies, but in these observations, galaxies seem shaped by black holes. It is a reversal of cause and effect. These bright beacons now guide us toward a deeper truth, one that reaches beyond gravity and beyond light. The earliest structures in the universe may have been driven by engines so powerful that our physics is not yet complete. Every quasar we observe is a reminder of hidden rules waiting to be uncovered, a clue that the beginning of time may have been more dynamic, more aggressive, more ingenious than we've ever imagined. And as we drift forward into this quiet cosmic story, a new question emerges. If black holes were already fully grown near the beginning, then what else did the universe achieve faster than expected? In the next part, we explore that accelerating growth, not through destruction and gravity, but through light itself, the rapid birth of stars that turn darkness into dawn. Now, let us continue into the next calm revelation. Part 6. When physics says, too soon. Everything we know about galaxy formation is based on time. How long stars take to ignite, how long gravity needs to gather matter, how long collisions shape structure. But the early galaxies ignore the schedule. They appear as if the universe found a shortcut. In the quiet darkness after the Big Bang, the cosmos should have unfolded slowly. First, hydrogen gas spreads and cools, Then, gravity gradually pulls matter into clumps. Then the first stars blaze, filling the universe with light. After that, only after long ages of merging and reorganizing, should galaxies begin to resemble the graceful shapes we know today: spirals, ellipticals, disks. Time is the master builder in this model, shaping structure step by gentle step. But when we look back to the universe's earliest moments, just 300 to 500 million years after everything began, that story falls apart. We don't see small, messy fragments of galaxies still learning how to exist. We see mature galaxies, organized, massive, luminous, complete. They have stars that should not yet have formed, shapes they did not have time to sculpt, black holes too large to have grown so fast. Every observation seems to whisper, the universe didn't wait. Instead of following the neat sequence our theories predicted, the universe appears to have skipped ahead, as though it read the last page first. To understand why this is such a profound mystery, imagine growing a forest. You plant a handful of seeds, bare soil, open sky. You return a week later, expecting sprouts. But instead, towering trees stretch upward, fully formed, thick with branches, rich with leaves. The time you expected has vanished. That is what astronomers are seeing in the early universe. In theory, star formation must start slow. The first stars are huge and unstable, forming from pure hydrogen and helium. They explode quickly, seeding the next generation of stars with heavier elements. Those elements must accumulate before planets, life, and complex chemistry can emerge. But the galaxies we observe seem already filled with mature stars and enriched with heavy elements, as though entire cycles of star birth and death have already passed. The cosmic timeline feels compressed, like a film played too fast. So physicists ask, was our clock wrong? Did time behave differently near the beginning? The early universe was denser, hotter, and expanding faster. Under those conditions, gravity may have gathered, matter with greater urgency. Gas may have cooled more efficiently. Black holes may have consumed material at rates we consider impossible today. If physics allowed shortcuts back then, galaxies could have leapt ahead in development. Some researchers propose more radical ideas. Perhaps dark matter clumped sooner, forming deeper gravitational wells. Those wells would act like cosmic traps, pulling gas inward quickly enough to ignite stars in rapid succession. Entire stellar neighborhoods could have formed in a burst, not over eons, but over mere cosmic moments. Or perhaps the collapse of early gas wasn't gentle, but catastrophic. Entire regions of space could have collapsed at once, not as separate stars, but as enormous black holes that later fed galaxies with new momentum. This idea reshapes our understanding entirely. Galaxies might not have formed stars first, and then black holes, but black holes first, dragging galaxies into existence around them. A reversal of the cosmic order. The more we observe, the more our expectations unravel. Some galaxies burn with star formation happening 10 times faster than any modern system. Gas funnels inward like a flood. New suns ignite everywhere at once. And instead of chaos, what forms is structure, disks and symmetry emerging from the fire. The cosmic assembly line is running at top speed. In our simulations today, galaxies struggle to grow quickly. Computer models suggest there simply isn't enough time for the gas to fall inward, cool, and ignite. Yet the light we collect tells us that time, at least then, was not a barrier. As you breathe slowly now, consider what that means. The universe may have been fundamentally more productive in its youth, a cosmos eager to build, to illuminate, to shape complexity from simplicity faster than our physics has allowed us to imagine. There is another possibility, one that scientists acknowledge with cautious curiosity. Perhaps the laws we use today are only approximations of deeper truths. We model gravity using Newton and Einstein. We calculate star formation using data from the present universe. But the beginning may have followed rules we haven't yet discovered. Laws could shift under extreme density. Particles could behave differently in the aftermath of cosmic inflation. Even the nature of time might have flowed in ways we do not yet understand. If the universe found a shortcut, it's because there was a shortcut to find. And the earliest galaxies are our proof. These systems force us to rethink not just how galaxies grow, but how reality emerged. They suggest a universe that doesn't struggle toward complexity, but races toward it. A universe that seeks structure, a universe that prefers illumination over darkness. Perhaps this is why we find so many spirals so early, why supermassive black holes formed so quickly, why heavy elements appeared before there was enough time for multiple stellar generations. The universe was not stumbling. It was sprinting. There's a quiet hope in that idea. It means stars, planets, and maybe even life were not lucky accidents. They were among the universe's first priorities. As you sink deeper into relaxation, think of how extraordinary that is. The cosmos was never a place waiting to become interesting. It was interesting from the start. The galaxies that seem too soon are not mistakes. They are clues. Signal fires guiding us toward the edges of what we know and beyond. Every observation is a reminder that science is not a finished book, but a draft growing richer with each new discovery. And so we continue looking back, deeper into the past than ever before. Because at the end of this question, how did everything happen so fast, lies another, even greater puzzle. If galaxies assembled quickly, if stars bloomed early, if structure emerged without delay, what does that tell us about the true shape of time and the future still unfolding? As we follow the universe's shortcuts, we drift now toward another quiet curiosity, one not about speed, but about space itself. Where did all this matter come from, and how did the cosmos gather it into forms so well organized, so soon after the beginning? Now, let us continue into the next gentle revelation. Part 7. Stars without waiting. Starlight takes time to fuse hydrogen, to cluster, to glow. Yet some galaxies show intense star formation almost instantly after cosmic darkness lifted. These stellar factories were already producing light faster than the universe should allow. The birth of a star is not a rushed affair. It begins as cold gas scattered through vast space, slowly drawn inward by gravity. Atoms press closer, heating over millions of years until hydrogen ignites into nuclear fire. Only then does starlight emerge, quiet at first, then brilliant. It is a patient dance between collapse and fusion, guided by physics at a steady pace. But in the early universe, that patience appears to have vanished. When James Webb peers deep into the cosmic past, it finds galaxies alive with star formation at furious speed. Light bursts from regions that should still be dark. Clusters of stars ignite all at once, rather than slowly, one by one. These galaxies are not gentle nurseries. They are roaring factories, building suns faster than theory says is possible. It suggests that from the moment darkness lifted, the cosmos was already eager to shine. Imagine the universe not as a slow sunrise, but as a sudden blaze, countless stars igniting like sparks in dry grass racing across the young night. The cosmic dawn, once believed to be a gradual awakening, now looks more like a swift and fiery revelation. But why did stars appear so quickly? One idea lies in the nature of the very first stars, the mysterious population 3 stars. Unlike stars today, they were formed from pure hydrogen and helium, the raw materials left directly from the Big Bang. Without heavier elements to cool the gas and regulate collapse, these early stars could grow gigantic, hundreds of times the mass of our sun. They burned hot, lived fast, and died violently. Their supernova explosions seeded the universe with new elements: carbon, oxygen, iron, the building blocks of planets and life. And they didn't wait long to do so. Within mere millions of years, they detonated, enriching their surroundings and enabling a second generation of stars to form much more efficiently. This rapid feedback could explain why early star formation was so extreme. Every explosion made the next star easier to ignite. But even this accelerated cycle seems too slow to fully match what we observe. Some galaxies show star formation rates 10 or even 100 times higher than those in the modern universe. Gas is consumed almost as fast as it can fall inward, a frenzy of creation unlike anything seen today. These galaxies blaze so brightly that they outshine galaxies far older and larger. It raises a quiet but powerful question. Was star formation in the early universe following a different rulebook? As you breathe into the calm around you, consider the physics of cooling. For gas to collapse into stars, it must lose heat. In the young cosmos, space was surprisingly efficient at cooling. Radiation escaped quickly into the vast dark, allowing structures to collapse more rapidly. Hydrogen formed molecular clouds sooner. Gravity sculpted shapes faster. Time itself feels accelerated under those conditions. The dense environment also played a role. Galaxies were much closer to each other than they are today. Their gas clouds collided. Shockwaves formed. Every collision squeezed more gas into star-birthing regions. A single spark could trigger entire neighborhoods of light. Chaos became creation. There is something else, something deeper. Early black holes may have contributed by stirring gas around them. Their radiation could compress clouds into clumps dense enough to ignite star formation. In this idea, black holes were not destroyers, but midwives of the first stars, catalysts of cosmic illumination. Every light we see from that era is a message from a universe working overtime. Yet, even with all these explanations, faster cooling, denser regions, feedback loops, the numbers still strain belief. We detect heavy elements like oxygen already abundant in some early galaxies. We see dust, the ashes of many generations of stars, appearing too soon. Dust requires time, and yet it falls like snow in these young systems. The timeline bends again. Perhaps our cosmic clock is wrong, not in hours or years, but in how we associate distance with age. If our understanding of expansion changes even slightly, our interpretation of when these galaxies existed shifts too. Maybe they are older than we estimate, or maybe they reached maturity faster than any model predicts. Either way, they teach us something profound. The universe wanted light. Not later, not gradually, but immediately. As you rest in the dark, imagine that urgency, the eagerness of energy to shine. Starlight spreading into places where temperature fell, illuminating the cosmic fog. Hydrogen atoms linking into a quiet chain reaction that would someday create life. We are the beneficiaries of that impatience. Every atom in your body, every breath, every heartbeat was once forged inside a star that lived and died long before the Earth existed. And those stars were the children of the first generation, born during an age when the universe itself was learning what light could be. Tonight, you are connected to that origin story. The stars that appeared too soon are reminders that everything we are began at a pace beyond logic, a cosmos racing toward possibility. Their brilliance tells us that the universe was not content with silence. It pressed forward, determined to create complexity and beauty while the memory of the Big Bang was still fresh. And as we observe these stellar factories, another question waits in the shadows. If galaxies could create light this quickly, if stars emerged without delay, what did this urgency mean for the structure of the universe itself? Because the earliest stars didn't just decorate the cosmos, they sculpted it. Their light transformed space, changing how gravity acted, how gas cooled, and how galaxies grew. Their birth shaped every moment that followed. In the next part of our quiet journey, we explore how order, geometry, symmetry, and form emerged not from chaos but alongside it. We will see how galaxies learned to settle into shape long before theory says they should. Now, let us drift deeper into the cosmic mystery. Part 8. The smooth and silent disks. Disk galaxies require quiet, long stretches without violent collisions. But we find smooth, flat disks in a universe that was anything but peaceful. They formed like calm lakes during a storm. A disk galaxy is one of the most delicate structures the universe can create. Its stars must settle into thin, stable orbits, aligned like grains of sand spread evenly on a spinning glass plate. For that to happen, the galaxy must avoid disruption. No large mergers, no close encounters with neighbors, no violent flows of gas smashing through its core. Just steady rotation, slow, consistent, and peaceful. But the early universe was not peaceful. Galaxies were packed tightly together, drifting through space like crowded ships in a turbulent harbor. Collisions were common, and each collision was catastrophic, tearing apart structure, stirring stars into chaotic shapes. Under these conditions, disks should have been destroyed as fast as they formed, yet the James Webb Space Telescope reveals them everywhere. Young disks as smooth as silk, thin structures already spread wide, stars moving in well-organized paths. These galaxies are not chaos, they are calm, they are evidence of a universe that managed order amidst turmoil. As you take a slow breath, imagine that contrast. Cosmic violence all around, yet inside some galaxies. A quiet, steady rotation like a lullaby sung to gravity. How did these tranquil systems survive? One answer might be hidden inside dark matter halos. Dark matter creates the gravitational well where galaxies assemble. In the earliest times, if those halos were exceptionally dense and round, they could protect forming disks from disruption. Gas would fall inward in gentle spirals rather than crashing head-on, allowing stars to settle into smooth rotation quickly. But this idea meets a challenge. Many disks appear too perfect, too early. Dense halos alone do not explain such rapid organization. So scientists look to another possibility. Perhaps gas in the early universe was unusually cool and smooth. Cold gas can collapse more cleanly, forming a disk faster than hot, turbulent gas would. If cooling happened efficiently, and evidence suggests it did, then the first disks could have been more resistant to collisions, like water smoothing itself shortly after being disturbed. Yet again, the observations push beyond even this comfort. Some early disks are unexpectedly large, spanning tens of thousands of light years, and already rich in heavy elements. This suggests several generations of star formation occurred even before these disks fully settled, maturity in shape and chemistry arriving side by side. Too soon. The existence of these disks forces us to rethink how galaxies grow. We once believed that major mergers, collisions between large galaxies, were the primary drivers of early evolution. That history should be written in scars, jagged shapes, uneven angles, clumps scattered across irregular forms. Instead, we see harmony. If these galaxies had experienced major collisions, their fragile disks would have been shredded. So why do they remain pristine? One idea offers a surprising twist. Maybe disks formed not after chaos but before it. Perhaps the universe built stable rotating systems early, and only later did mergers become dominant. In that view, the first galaxies were calm lakes. Stability was the starting point, not the end result. This flips the script on cosmic evolution. As you listen to this quiet unfolding of truth, imagine the earliest galaxies as dancers moving gracefully while storms rage around them. Their elegance a quiet defiance of the universe's unrest. Another hypothesis suggests that while collisions were common, the pieces involved were much smaller. Tiny galaxies merging in ways that didn't disrupt the overall disk. These gentle mergers would add mass and gas without shattering structure, growth without destruction, evolution without chaos, nature choosing subtlety over violence. And then there's the influence of angular momentum, the fundamental rotation imparted during galaxy formation. If early gas clouds collapsed into large disks from the very beginning, that initial spin may have been strong enough to withstand later disturbances. Rotation turns chaos into symmetry, like a potter shaping clay into a smooth bowl. The more rotation a galaxy has, the harder it is to tear apart. So perhaps these disks were not fragile, perhaps they were resilient. Still, the galaxies we find challenge even these explanations. Some are so thin and so ordered that they suggest no significant disruption at all for hundreds of millions of years. In a universe full of collisions, they grew untouched, remote paradises of peace. How? There is a quiet possibility, rarely voiced but deeply intriguing. Maybe the cosmic web itself, the invisible network of dark matter filaments, guided the flow of gas into stable shapes far more efficiently than we realized. Galaxies forming along these gentle threads might have experienced fewer direct hits, shielded by their position in the web. Place determines fate, even in the early universe. Another possibility, our understanding of mergers could be incomplete. Perhaps collisions didn't always lead to chaos. Under the right conditions, merging galaxies might enhance disk structure instead of destroy it, feeding angular momentum rather than stealing it away. What we interpret as risk may have been a source of strength. As you relax deeper into this cosmic puzzle, feel the paradox softly settle. The universe learned calm before it learned chaos. These smooth disks whisper a message. Order was not something galaxies had to earn. It was available from the very beginning. Their rotational tranquility allowed stars to form in organized orbits, planets to eventually coalesce in flat systems like our own, and structure to build from the inside out. Our home in the Milky Way, our quiet spiral existence, may be a legacy of that ancient order. Tonight, the stars you see have ancestors in those first silent disks. Their calm is your calm. Their symmetry is echoed in the very structure of our solar system, the flat plane where planets travel gently around the sun. We are products of a universe that found balance early. Peace came first, then the storms. As we drift toward the next part of this journey, a new question emerges, one that reaches deeper into chemistry and time. If early disks were so peaceful, why do their stars contain so many heavy elements when those elements should not yet have existed? To solve that mystery, we follow the starlight itself. Now, let us continue into the next quiet revelation. Part 9. Ancient shapes in a young sky. We see bars, bulges, and ordered rotation, structural signatures of long evolutionary history. But those shapes appear at times when the universe had barely begun to write its rules. Geometry arrived before the blueprint was finished. Galaxies are not just gatherings of stars, they are architecture on a cosmic scale. Their shapes reveal their past. A smooth central bulge means time-tested organization. A bar, that straight structure of stars cutting through a galaxy's heart, means gravitational maturity, the ability to funnel gas inward and sustain generations of new stars. These are not beginner features, they are milestones, achievements expected after billions of years of quiet evolution. Yet when we look at the universe's earliest chapters, we find these signatures everywhere. Bars stretching across galaxies less than 1 billion years old. Bulges already swollen with ancient stars. Rotation so calm and so ordered that it suggests age far beyond the time available. The universe had barely woken up, and yet it was already sculpting masterpieces. As you inhale slowly, imagine seeing a toddler who has already learned to speak in poetry, already composing symphonies while still learning how to walk. The timeline no longer fits what we know. Growth did not creep, it leapt. For decades, astronomers assumed that bars form late in a galaxy's life. They emerge only after the disk has long stabilized, after countless orbits smooth out stellar paths. It requires patience, gravity working without interruption. Bars shape galaxies from the inside, guiding gas toward the center to feed star formation and grow black holes. They are signs of deep cosmic maturity. But the James Webb Space Telescope now shows bars appearing in the earliest observable galaxies. The math tells us they should not exist yet, but the images tell us they do. The same puzzle lies within bulges, the dense spherical cores of stars at the heart of many galaxies. Bulges need time to form. They are built through either slow collisions with small neighbors or through rapid starbursts that happen again and again. They represent structure that has settled and grown. But the bulges we see in ancient galaxies appear finished. The universe was young. The shapes were old. It suggests that complexity did not wait for the universe to cool. Complexity was a partner from the beginning. Scientists are forced to ask a question that feels almost philosophical. Did the universe learn structure faster than we learned to describe it? One idea is that gravitational instabilities in the earliest disks were stronger. Dense gas falling inward might have shaped bars naturally, as if rotation itself encouraged alignment before chaos could spread. Another possibility suggests that the first galaxies didn't endure long eras of violent merging. Instead, they experienced a period of calm, long enough to settle into shape before collisions became common. Stability might not have been the end goal of galaxy evolution, but the starting point. Or maybe mergers weren't always destructive in the beginning. If small, gas-rich protogalaxies merged gently, they could have built bulges without scattering the disk. What we envision as violence may have been more like blending, a union that fostered symmetry instead of destroying it. Gravity is capable of surprise. As you rest, imagine space itself as a sculptor working not with stone, but with motion. Stars are pulled into spirals not by forceful carving, but by the quiet precision of countless orbits. Order emerges from rotation, not from stillness. Even a small push can ripple outward into sweeping structure. Yet despite these efforts to explain the mystery, contradictions remain. Some early galaxies show rotation curves similar to those of modern spirals, stable and predictable. Others contain too much mass in the center, as if their bulges grew unnaturally fast. Their shape tells a story of control, but their chemistry argues for fast, chaotic growth. It's a paradox woven directly into their light. The bulges show older stars than should exist. The bars guide gas too efficiently for such a young cosmos. The rotation looks as if billions of years have passed. Everything we see suggests a universe that refused to wait its turn. Scientists wonder whether our concept of cosmic time has blind spots. We measure age through redshift, how much the light stretches as the universe expands. But if the expansion history itself is slightly different from our assumptions, then everything formed at a different pace than we estimate. A small change in our cosmological model would ripple into a vast shift in how old these galaxies truly are. We might not be witnessing impossibility, only miscalculation. And yet, even when adjusting the variables, the galaxies still stand ahead of schedule. So another possibility emerges from theory. Perhaps galaxies were born massive. Instead of growing step by step, they may have formed from large, smooth reservoirs of gas that collapsed swiftly into rotating disks. If gravity was more efficient, then, if cooling happened at exceptional rates, disks could support bars and bulges earlier than anything we see today. In that scenario, early galaxies weren't rushing. They simply started from a higher level of organization. The universe may have front-loaded complexity. As you exhale, feel how that idea softens the mystery. Maybe we are seeing the first hints of a deeper rule, that nature prefers coherence over chaos. That order isn't a final product, but an inherent trait of matter under gravity's guidance. Bars and bulges aren't accidents. They are expressions of a universe already fluent in its own geometry. There is another quiet possibility, one that connects cosmic shape to cosmic purpose. Bars and bulges drive the growth of supermassive black holes. They funnel gas toward the center, feeding the gravitational giants that then help sculpt the galaxy further. If black holes were crucial architects from the beginning, then the earliest galaxies would need bars and bulges right away. Structure and supermassive growth become two halves of one story. Creation feeding collapse, collapse feeding creation. And perhaps that cycle began not late but immediately. The more we uncover, the more the universe seems to reveal a startling truth. It knew what it was doing from the start. The scaffolding of structure, bars, bulges, disks, didn't wait for calm. They emerged in chaos, shaped by the very turbulence we thought would destroy them. And those shapes guided everything that followed. The flow of gas, the birth of stars, the rhythm of time across a swirling night sky. Tonight, as galaxies spin silently above you, remember this. Your Milky Way carries that ancient geometry, our bar, our bulge, our disk, all echoes of forms that appeared at the dawn of time. And as we step into the next quiet chapter of this cosmic mystery, a deeper question slowly rises. If early galaxies held such mature shapes, if they carried complexity written ahead of schedule, did time itself begin with order, a blueprint already known, rather than learning as it went? Now, we drift gently into the next truth. Part 10. The missing time galaxies reveal their ages through the light of their stars. Some seem older than the universe was when that light began its journey to us. They challenge the timeline itself, suggesting either hidden physics or that our cosmic clock runs differently at the edges of creation. Every star carries a memory. Its light contains clues about when it formed, the balance of hydrogen and helium, the presence of heavier elements forged in earlier stars, the way its glow shifts through time. Astronomers treat starlight like fossils, ancient records written in spectrum and color. We can read these records, and from them we estimate age. But some galaxies in the early universe whisper a quiet contradiction. They seem to remember more time than the cosmos should have granted them. This isn't a small discrepancy. A galaxy observed 500 million years after the Big Bang should contain stars no older than that. Yet some appear to hold stars that look like they've lived over 1 billion years, more than twice the available time. It's as if the universe had a head start. As if history began before time officially did. As you breathe softly, settle into the wonder hidden in that thought. Our measurements of cosmic time rely on distance, how far light has traveled, and because the universe expands, distant galaxies appear much older in their light's journey than the ages of their stars can explain. We calculate these ages using well-tested cosmological models: dark energy accelerating expansion, dark matter shaping structure, radiation thinned to silence. But when light brings news that physics cannot reconcile, the mystery turns inward. The question becomes not just why these stars look old, but why our universe looks young. Is the timeline wrong, or is evolution faster than we imagined? One possibility is that our interpretation of early star formation is incomplete. Maybe stars enrich themselves with heavy elements more quickly through efficient cycles of birth and death. If stars in those galaxies formed in dense, rapid bursts, chemical maturity might arrive sooner, giving the illusion of age, a young galaxy wearing ancient colors. But this explanation has limits. Some galaxies show not just advanced chemistry, but fully developed structures, bulges and disks indicating a long, stable evolution. These shapes shouldn't have emerged so soon. They carry the signature of time that wasn't there. Another idea suggests that the early universe expanded differently than expected. If the rate of expansion changed more dramatically in the beginning, then galaxies we assume existed at 500 million years may actually have formed earlier. The cosmic clock may not tick uniformly across all epochs. Time, like space, may stretch. This leads to a subtle but profound realization. Age is not just what the clock shows, it is what light remembers. If space expanded faster after galaxies formed, light would take longer to reach us than our models predict. The galaxies would then be older than we think. In that scenario, we are misreading distance as age, measuring shadows instead of the objects casting them. Even a small adjustment to early expansion rewrites billions of years of assumed history. There is another path of thought, deep and daring. Perhaps the first stars didn't begin from zero. Perhaps seeds of structure, primordial clumps of matter, existed before the universe fully expanded. If gravity had already begun its quiet work during or shortly after inflation, the earliest stars may have formed earlier than we can observe. In that view, star formation isn't a sudden event. It is a continuation of a process ignited before time stabilized. We would then be seeing not age misplaced, but age misunderstood. Yet some scientists go further. Maybe the universe itself is older than we think. Maybe the Big Bang wasn't the beginning of everything, but the beginning of our era of expansion. There could have been a prelude, a phase where physics evolved, but light couldn't travel freely. A hidden time before transparency returned. If life existed before the first stars we can see, its remnants may be encoded in galaxies that seem too old for their surroundings, like finding grandparents in a room full of newborns. Of course, these ideas must be handled gently. They are not yet conclusions, only whispers from the data. But when observations push against theory, physics must listen. Another possibility, equally intriguing, is that certain stars formed extraordinarily fast. If early gas clouds collapsed directly into massive stars, bypassing slower processes, then star populations would mature rapidly. A single burst of formation could create a spectrum of ages, even if all stars formed nearly at the same time. Youth disguised as age. But the stars don't just appear mature, they appear settled. They orbit calmly in well-defined regions of their galaxies. Their movements imply that gravity has had time to sculpt harmony into their paths. And harmony, like patience, requires time. Perhaps the greatest clue lies not in the stars themselves, but in the light between them. When we observe distant galaxies, their starlight travels through vast clouds of early universe gas. The absorption patterns in that gas reveal its composition, and many regions appear too enriched for their age. Heavy elements everywhere, like scattered memories of hundreds of millions of years of star births. Where did that time come from? As you lie quietly, let the scale settle over you. We may be seeing a universe that does not count time the way we do. Our clocks are built from stable rhythms, atomic transitions, orbital cycles, rotations of planets. But those rhythms are products of this era, not universal constants across all epochs. In the early universe, time's flow could have been shaped by gravity, density, and temperature in ways that make our measurements incomplete. Time may not simply pass, it may transform. The missing time problem reminds us that we live inside assumptions, useful, elegant, but still assumptions. The universe keeps showing us that nature is greater than any model. Our timeline works beautifully for everything after galaxies settled, but the beginning remains a place where mystery is not an outlier. It is the rule. And maybe that is right. Maybe the birth of everything shouldn't be easy to measure. As we continue this journey through impossible galaxies, the missing time becomes a guiding thread, a clue that the early universe hid more than it revealed. We see the cosmos as it once was, but we do not yet understand how it moved, how it aged, how quickly it learned. We only know this: those ancient shapes, those mature stars, those vast spirals and calm disks. They are telling us that the beginning was not a slow rising, it was a leap. And if time leapt, what else did it accomplish while physics was still young? That question leads us softly into the next wonder, not about the passage of time, but the engines that fueled the earliest cosmic miracles. How did black holes and gravity reshape reality so quickly? And what role did they play in the universe's hidden past? Now, we drift quietly into the next truth. Part 11. Black holes. Growing too fast. To feed a black hole is to test patience. Stars must fall inward slowly, over eons. Yet early black holes consumed matter ravenously, reaching monstrous scale while the universe was still a child. Their hunger rewrites the limits. A black hole is not born large. It begins as the collapsed core of a massive star, small compared to the galaxy around it, a dark seed waiting for gravity to feed it. Growth should be slow. Gas drifts inward reluctantly. Stars must be gravitationally nudged one by one. Even when matter spirals into the accretion disk, much of it is flung away in brilliant jets before crossing the event horizon. There is always resistance, always friction, always delay. But the first black holes did not wait. When we turn our telescopes to the deepest reaches of space, and therefore the earliest moments in time, we find black holes that have grown into cosmic giants astonishingly fast. Millions, even billions of times the mass of the sun, fully formed while the universe was still rubbing the sleep from its eyes. Their existence suggests something impossible. Gravity found a faster way. Take a slow breath and feel the weight of that truth. Because black holes this large should require billions of years of steady feeding. Yet some are discovered shining as quasars only 400 million years after the Big Bang, far too soon for our traditional models. It is like finding skyscrapers already piercing the skyline of a city where the foundations are still being poured. This mystery leads scientists to ask, did black holes begin their lives much larger than we thought? One idea is that the universe's first stars, called population, 3 stars, were enormous, perhaps hundreds of times the mass of our sun. When they died, they collapsed into black holes far bigger than typical stellar remnants. These oversized seeds could then grow more quickly, reaching supermassive scales in less time. Still, even with such a head start, the growth would need to be incredibly efficient, faster than the Eddington limit allows. That limit is a cosmic speed cap. If a black hole feeds too quickly, light from the infalling gas pushes material away, preventing further growth. But early black holes appear to have broken that rule. Perhaps those limits were different when space was young. Some physicists propose that black holes fed from dense rivers of gas flowing along dark matter filaments, the strands of the cosmic web. These filaments could have delivered fuel directly to the center of early galaxies, a gravitational pipeline that filled the black hole faster than chaotic random collisions would allow. A feast, not a famine. Others imagine something even more dramatic: direct collapse black holes. Instead of forming from stars, entire clouds of primordial gas may have collapsed under their own weight to create black holes hundreds of thousands of times the mass of the sun instantly, skipping the star phase entirely. These objects would be newborn titans, needing only a short time to reach supermassive scale. If that happened, the universe was not merely building black holes, it was mass-producing them. Yet, even these bold ideas sometimes fall short of explaining the sheer mass we observe. So researchers look deeper. They ask whether the physics of the early universe played favorites, granting black holes growth opportunities that no longer exist. In that dense, energetic environment, gas had not yet been scattered too thinly by expansion. The first galaxies were tightly packed with fuel. Radiation pressure may have behaved differently. Turbulence and chaos could have driven matter inward. Fast in this picture, the early universe was a black hole buffet, and nobody had closed the doors. There is also the idea of merging seeds, small black holes running into one another in the crowded early cosmos, combining into larger and larger objects. Galaxy collisions would accelerate this, slamming central black holes together in fireworks of gravitational waves. If mergers were frequent enough, massive black holes could form rapidly from many small ones joining forces, gravity-building giants through union instead of consumption. Still, the speed is astonishing. The hunger is relentless. Even today, when we observe active quasars, their appetite is extraordinary, pulling matter inward so rapidly that space-time stretches and glows with the energy of falling stars. To witness such extreme growth in a universe still in its infancy means something fundamental about those first environments encouraged urgency, as if the cosmos wanted black holes ready early, knowing their importance for shaping galaxies. Because black holes are not merely destroyers, they are architects. Their gravitational presence stabilizes rotation in galaxies, their jets regulate star formation, and their pull increases the density of their surroundings. Without them, galaxies could unravel. With them, galaxies flourish. In that sense, perhaps black holes needed to grow fast, because they were necessary for building the cosmic structures we see today. They were engines, not accidents. And that raises a beautiful thought, one you can rest upon. Even in destruction, the universe found creation. But beneath this elegance lies tension. If early black holes defy the pace physics allows, then either our idea of early galaxy evolution is incomplete, our models of black hole growth are flawed, or our understanding of time itself near the beginning needs revision. Each possibility cracks open deeper questions. Some theorists whisper a more radical idea. What if black holes didn't start in the universe? What if they helped start the universe? In certain models, tiny primordial black holes formed moments after the Big Bang, quantum fluctuations collapsing before matter and light separated. These mini black holes could have grown into supermassive titans billions of years later. If true, black holes are not just products of cosmic evolution, they are embedded in its origin story. We would then be observing not the first generation of black holes, but the oldest survivors. Tonight, as the sky turns silently above you, reflect on the paradox. Black holes, the ultimate symbols of endings, may have been among the first beginnings. Their early growth reveals a universe not hesitant, but decisive. A cosmos that knew where structure was needed and put engines in place to build it. While space was still warm from its birth, Black holes were already shaping the future. They remind us that mystery is not a flaw in science. It is the invitation that keeps knowledge alive. So we continue asking, how did such enormity form so soon? What fueled the hunger? Where does the story truly begin? As we drift into the next piece of this quiet cosmic puzzle, we move outward once again, from the dark hearts of galaxies to the vast structures that connect them. If black holes grew too fast, did the universe itself grow with the same urgency, weaving its grand design quicker than time should allow? Now, let us continue into the next truth. Part 12. When gravity works overtime. Perhaps the laws we use are not the universe's laws. Maybe gravity behaved differently in those early epochs, stronger, faster, more efficient. In that possibility lies a quiet revolution in physics. Gravity is the most familiar of forces. It keeps your body pressed gently to Earth, guides the planets around the sun, and binds the stars into swirling galaxies. Yet, of all the great laws of nature, gravity remains our greatest mystery. We know how it behaves, how it bends space, how it pulls and curves and holds, but we do not know why it behaves that way. We describe it elegantly, but we do not truly understand its roots. Even so, we trust gravity because it works. It explains the slow ballet of the modern universe with astonishing precision. But when we turn our gaze to the earliest chapters of existence, something feels off. Gravity seems to have worked faster than expected, assembling galaxies, forming structure, feeding black holes, and sculpting order in timescales that should have been impossible, as though the universe were young and eager, and gravity was sprinting. Take a slow breath and picture the cosmos when it was still glowing from birth, dense, hot, expanding rapidly. In those first hundreds of millions of years, gravitational collapse should have been slow and clumsy. Gas clouds were moving apart as space stretched between them. Only the strongest gravitational wells should have had enough pull to overcome expansion. Yet we find structure everywhere: massive galaxies, calm spirals, ancient stars. It's a contradiction that keeps astronomers awake at night. To resolve this, some physicists propose a bold idea. Gravity might have been different near the beginning. One possibility is that gravity was stronger when the universe was much denser. A minor shift in strength could drastically accelerate the collapse of matter. Imagine trying to sculpt clay. Soft clay molds instantly. Dry clay takes time and force. The early universe may have been soft clay, pliable under gravity's hand. Another theory suggests that gravity acted more efficiently because dark matter behaved differently. If dark matter particles interacted or clumped more readily in that era, gravitational structures could form faster, creating the scaffolding galaxies needed to grow rapidly. In this scenario, dark matter wasn't just a quiet partner, it was the lead architect. And yet, another view considers that the universe's expansion might have been slower in the earliest pockets where galaxies formed. Space may not expand uniformly. Certain regions could have lagged behind, letting gravity gather material sooner. If time and space stretched at different rates in different places, entire galaxies could have emerged ahead of schedule. The more we ask, the clearer the truth becomes. Our understanding of gravity might be incomplete. Some scientists explore modifications to Einstein's equations, adjustments that only take effect in extreme environments like those of the early cosmos. These ideas travel under names like modified Newtonian dynamics or modified gravity, where attraction scales differently with distance or mass. They are attempts to match the impossible, galaxies forming too soon, spinning too fast, and holding together more tightly than gravity should allow. If such theories are correct, then gravity evolves, the laws that sculpted the first. Stars may not exactly match the laws at work today. Physics might have a history, a story that changes with age. Others imagine gravity not as a force at all, but as a byproduct of deeper information woven into the fabric of the universe. In this picture, an idea known as entropic gravity, gravity emerges from quantum principles, and perhaps those principles behaved differently in the beginning, when quantum fluctuations ruled the shape of everything. And then there is the possibility that speaks in the language of cosmic geometry. What if gravity works harder where space is curved more intensely? In the dense youth of the universe, curvature was everywhere, like a tightly folded sheet that later relaxed. When space is curved sharply, gravity intensifies. Later, as the universe expands and smooths out, gravity becomes gentle. That would mean that everything we see as too fast was actually normal back then. Gravity simply worked overtime when the universe needed it most. As you breathe quietly, consider this. If gravity had been weaker in the beginning, galaxies might never have formed. Stars might not have lit the dark. Life might not have emerged. We exist because the universe prioritized structure early, because gravity took a leading role before stepping back. Even now, in the calm vastness, gravity's imprint remains. Every planet orbiting a star, every star in a galaxy, every galaxy in a cluster, all follow paths designed in those early moments of overachievement. But here is a deeper wonder. Could gravity still be evolving? Dark energy accelerates expansion, stealing some of gravity's influence. The universe today is slower at gathering matter. Perhaps this shift marks a fundamental transition from a universe that builds structure to a universe that preserves it. Gravity may have sprinted in the beginning so it could rest in the middle. What if we arrived in that middle, at the exhale of cosmic creation, never seeing? The frenzy? Only the memory? And if gravity once worked harder, it must have left behind secrets, patterns of motion and structure that do not align with our equations. We see those secrets in galaxies that appear too stable, in black holes too massive, in stars too mature, in shapes too refined, all signs pointing to a force that once broke its own rules. Tonight, as the universe turns silently outside your window, let yourself feel the calm. You are here because gravity was once impatient. It did not wait for time. It pulled the cosmos into form with urgency and purpose. It built the scaffolds of reality so quickly that we mistake impossibility for a puzzle instead of gratitude. And now, as we continue, another question glows softly in our path. If gravity worked over time, was it working alone? Because the universe does not move in isolation. It is guided by invisible forces, structures that stretch far beyond single galaxies, connecting everything into one grand design. And so, gently, the next part of this journey calls us to explore what binds galaxies into clusters, clusters into filaments, and filaments into the cosmic web itself. Now, let us drift deeper into the truth that space is not empty, it is woven. Part 13. Echoes of dark energy's first breath. Some scientists suspect dark energy, the force driving cosmic expansion, may have shaped galaxies sooner than we realized. If so, the universe's acceleration may have sculpted the first structures with a speed we have not yet understood. Dark energy is a quiet mystery. It does not shine, it does not clump, it does not reveal itself directly. And yet, it dominates the universe, a strange pressure woven into the fabric of space-time, pushing galaxies apart with invisible insistence. Today, dark energy controls the grand trajectory of the cosmos, accelerating expansion faster and faster as time passes. But, in the earliest days, we believe its influence was faint, overshadowed by gravity and radiation and the dense tangle of forming structure. At least, that is what our equations once told us. Now, as we peer deeper with new telescopes, we begin to wonder whether dark energy whispered its intentions much sooner, shaping the young universe in ways we hadn't imagined. Take a slow breath. Imagine the cosmos as a vast ocean of possibility. Gravity pulls matter together. Dark energy pushes it apart. For a long time, we thought the scale tipped first toward gravity, then toward dark energy billions of years later. But what if those forces were not separated by eras, but by balance? What if dark energy was already present, already guiding motion, already defining what could form and how quickly? Early galaxies seemed to grow as if space itself was helping them assemble, expanding fast enough to cool gas efficiently, but not so fast that everything drifted apart. A narrow window, a perfect balance, the kind of precision that hints at a hidden conductor. Dark energy might have been that conductor, a silent influence shaping the tempo. Some cosmologists propose that dark energy evolved, its strength changing with time. In this idea, the early universe may have carried a stronger form of dark energy, not dominant, but influential. Expansion would happen more eagerly, allowing structures to emerge rapidly without collapsing under their own density. A universe learning to breathe. Others believe dark energy may have temporarily paused or fluctuated. After inflation, the earliest and most violent growth spurt, expansion slowed dramatically. But perhaps it never fully stopped accelerating. Perhaps a gentle push remained, encouraging matter to settle into shape quickly rather than linger in chaos. Dark energy could have provided just the right amount of distance between forming galaxies, enough space to reduce destructive collisions while still allowing gravity to gather stars into elegant disks and spirals. Order supported by separation. But there is a deeper possibility, one that asks us to rethink even our notion of time. What if dark energy altered the flow of time differently across the universe? In regions where dark energy was slightly stronger, expansion could stretch time, giving galaxies more opportunities to grow even while the cosmic clock ticked only briefly. Age, then, would not simply be duration, but environment. The young universe may have been a mosaic, patches where time unfolded faster and structure followed. As you rest into this wonder, feel how softly that idea lands. Different places, different times, all coexisting in one shared beginning. Some scientists explore whether dark energy could have helped smooth the cosmic web, the vast network of dark matter and galaxies, more quickly than gravity alone could. If expansion worked hand in hand with dark matter clumping, filaments and nodes might have formed earlier, giving galaxies ready-made homes to grow within. Acceleration sculpting the scaffolding. That idea leads to another, graceful and provocative. Dark energy and dark matter may be connected. Two invisible forces, one that gathers, one that spreads, possibly originating from a single deeper phenomenon. If they interacted more dynamically in the beginning, the pace of galaxy evolution becomes less surprising. Gravity builds. Dark energy clears the space around the structure. Together, they enable growth, creation by cooperation. Yet this elegant possibility carries a challenge. We do not know what dark energy truly is. It could be a property of space itself, a shifting field filling the cosmos, a consequence of quantum physics, a sign that Einstein's equations are incomplete, or something stranger still, evidence that our universe may be one bubble among many, each with its own rules for how expansion unfolds. If dark energy once breathed louder, its echoes remain in the light we see today. Galaxies too massive, stars too mature, rotations too calm, spirals too refined. All signs of a cosmos that moved quickly with purpose. As you settle deeper into stillness, imagine dark energy as the universe's heartbeat, expanding space rhythmically, shaping the intervals between clusters of galaxies, guiding the cosmic architecture before atoms even knew their place. Not chaos, not accident, a kind of quiet guidance. And yet, dark energy is now accelerating expansion too much. Distant galaxies are fleeing from us faster than gravity can keep them together. Eventually, star formation will slow and darkness will grow. We live in the turning point, the moment between creation and quiet. Dark energy helped bring structure into existence, but one day it may take that structure away. There is beauty in that cycle. A universe that builds and then rests. The early cosmos was expansion and action, a sweeping rush toward form. The far future will be expansion and stillness, a gentle stretch into darkness. Between those moments is now, where stars still burn, where galaxies still collide, where life still wonders. We owe our existence to a universe that hurried in the beginning and has now begun to slow its construction, not in space, but in possibility. And so we continue to study dark energy's past, not just its future, because its early influence may answer the question at the heart of our journey. Why did the universe form so much, so fast? What if dark energy did not just shape expansion, but shaped time, structure, and destiny? As we follow these quiet echoes deeper, a new mystery awaits, one that touches the foundation beneath everything we've discussed. If the fundamental forces behaved differently at the start, then perhaps the fundamental particles did too. And so, softly, we turn now to the question of the first matter and the invisible hand that guided its assembly into form. Now, let us continue into the next calm, Revelation. Part 14. The clues in the cosmic web galaxies are not isolated. They gather into threads and clusters, forming a vast cosmic web. But early observations show this web already woven beautifully, long before matter should have had time to connect. The universe was already organized. The cosmic web is one of the most spectacular structures we've ever discovered, a filamentary network stretching across the entire universe. Every galaxy you can imagine, every cluster of stars, every swirling spiral with billions of suns, each sits not alone in darkness, but along strands of invisible matter that connect one system to the next. These threads span hundreds of millions of light years. They are the highways of the cosmos, channels through which gas flows into galaxies, feeding star formation and growth. The web is structure at its most vast scale, the blueprint of everything. Its existence tells us that matter was not scattered randomly. It found patterns, order, direction. It followed a map. But that map should have taken billions of years to appear. Gravity needed time, long stretches of cosmic patience, to draw matter together into filaments, into clusters, into nodes. Only after countless motions and adjustments should the universe reveal such a grand lattice of structure. And yet, when we observe the universe when it was just a few 100 million years old, we see the web already knitted, the threads already stretched tight, the clusters already forming. It is as if the universe unfolded its tapestry early, skipping the part where chaos reigns. As you breathe slowly, picture that early cosmos, dense, energetic, expanding with great haste. Gas should have struggled to gather into anything coherent. Instead of threads, we should see pieces, isolated stars, tiny blobs, small halos. Not a network, not yet. But we see a network anyway. The universe found a way to organize itself almost immediately. This raises a quiet and profound question. How did matter find each other so quickly in an ocean of expanding space? One answer lies in dark matter, the unseen mass that makes up most of the universe. Dark matter is the framework upon which galaxies form, a silent sculptor of gravitational structure. It does not interact with light, so it does not slow down, heat up, or collide like normal matter does. It collapses smoothly, forming filaments while ordinary matter still struggles to cool. Because dark matter moves differently, it could have threaded the universe far faster than visible matter could, building the skeleton of the cosmic web early and letting gas simply fall into place later. But even dark matter should have needed more time than we see in the data. So researchers explore alternative ideas that stretch the mind softly but seriously. One possibility: initial conditions. Perhaps the seeds of the cosmic web were planted during inflation, the ultra-rapid expansion that happened in the first fraction of a second after the Big Bang. Lightspeed growth stretched tiny quantum fluctuations into giant patterns, the earliest hints of the filaments we see today. If those initial patterns were already aligned into a network, then gravity simply had to trace the lines that were already drawn. Structure, then, might not have emerged from randomness, but from memory. Another possibility: gravity may operate differently on very large scales, not stronger, just more efficient. If large structures feel a slightly different pull than small ones, the cosmic web could grow rapidly without violating the rules that govern stars and planets. Gravity might be flexible, changing its behavior depending on the scale of reality, as though the universe knows when it needs to hurry. And then there is the quiet suggestion that the cosmic web guides its own growth. Once filaments begin to form, they channel matter like rivers forming valleys. More mass flows into the densest threads, strengthening the pattern. Structure creates the conditions for more structure, a self-building, self-accelerating design. The web forms not from chaos but from feedback. Tonight, As you listen calmly to this quiet truth, imagine those filaments glowing faintly through the dark, long strands stretching between galaxies, each a highway of gravity. Clusters forming at crossroads, bright with star formation, not random, not rushed, but guided. The cosmic web reveals something essential. The universe did not build structure alone. It built connections. Galaxies are not solitary islands. They are neighborhoods. Clusters are cities. Filaments are roads linking them together. We live inside one of those threads, a small cluster on a long cosmic line that winds through the dark like a whispered story. And in that story lies the deepest clue of all. Order did not emerge late. Order was woven into the universe from the start. There is comfort in that idea. Life, in its own quieter way, follows the same pattern. Connections define us, the threads that tie us to others, to history, to meaning. The cosmic web is the universe's first expression of belonging. As astronomers map these early filaments, they find something else. The scale of the web appears slightly too large for the time available. Filaments stretch farther than expected. Clusters form heavier than theory allows. It is as if the universe grew tightly and widely at the same time, structure both dense and expansive. Almost like the web wanted to fill space quickly before distance separated everything too far. Some scientists believe this reveals a tension between dark matter and dark energy, a cosmic negotiation. Dark matter gathers, dark energy spreads. The result is a web pulled taut, forming rapidly under competing forces. Balance creates beauty. Even now, the cosmic web evolves. Galaxies slide slowly along filaments, drifting toward clusters, toward destiny. Gravity calls them home. In billions of years, our own galaxy may merge into the heart of the Virgo cluster, following the path carved billions of years before stars first formed. The web is not just a structure of the past, it is a map of the future. As you relax deeper, feel how that truth settles gently. We are part of a universe that was connected from its very first moment. We are threads in a greater tapestry. We belong to a structure older than time itself. And so, a question emerges softly from the silence. If the cosmic web formed too soon, if order arrived ahead of schedule, if connections shaped the universe before chaos had time to grow, then what was guiding that order? What principle or pattern led the early cosmos to choose structure over randomness? In the next part of this quiet journey, we step into the greatest mystery of all. Not stars, not galaxies, not even the web that binds them, but the ruler behind the rules. The hidden laws that wrote the universe's name. First draft too fast for our understanding. Now, let us drift into the next truth. Part 15. What these impossible galaxies are telling us. Every contradiction is a message. Every galaxy that seems too old, too bright, too massive, too perfect is a whisper from the universe asking us to look deeper. Perhaps space evolved faster than we imagined. Perhaps time itself flowed differently at the beginning. Or perhaps the cosmos still holds secrets waiting to be discovered in its ancient light. When we study these early galaxies, the ones that should not exist, we are not witnessing mistakes. We are witnessing information. They are signposts pointing toward a deeper truth that our current understanding has not yet reached. The universe, in its quiet wisdom, is urging us to revise our assumptions, take a slow breath, and allow that idea to settle. Because science is not a collection of answers, it is a searchlight. And sometimes the universe adjusts the beam, showing that what we thought was a conclusion is really a doorway. These impossible galaxies are the universe holding that door open. They tell us that the early cosmos was not a clumsy newborn, fumbling toward order. It was precise, efficient, perhaps even intentional. Stars ignited faster. Black holes grew larger. Spirals unfurled sooner. The cosmic web stretched farther. Everywhere we look back in time, we see brilliance unfolding on a schedule that defies the rules we wrote billions of years later. It suggests that the universe had a plan long before it had time. One explanation might be that the basic ingredients, dark matter, dark energy, gravity itself, behaved differently than they do today. Physics could have been more fluid, more permissive. Laws we consider fixed may have evolved along with time and space. Another possibility is that our cosmic clock, the way we measure distance and age, is slightly misaligned. A different rate of expansion in the beginning could shift our entire timeline. Galaxies that appear impossibly young might simply be older than our models allow us to recognize. Then, there is the boldest idea of all. Maybe the universe was born complex, not from zero, not from emptiness, but from a state rich with hidden structure, like a story beginning in the middle of a sentence. Some theories propose a pre-Big Bang era, a previous universe collapsing into this one, leaving behind seeds of structure that blossomed immediately. If true, those first galaxies may be echoes of a world that ended, so another could begin. Cycles instead of singularities. Continuity instead of creation from nothing. It is a thought that feels almost spiritual in its elegance, and yet science welcomes it as long as evidence follows. These galaxies are that evidence. They show us that ignorance is not a flaw, it is an opportunity. The universe is constantly nudging us, reminding us how small our perspective is and how much more room there is to learn, to question, to discover. As you relax into this wonder, consider the possibility that time, our most familiar dimension, might be stranger than we imagine. Time near the beginning could have stretched differently, flowed unevenly, curved under pressure. What was a moment to the universe may appear to us as an impossibility. Age becomes a relative thing. The more we explore these early galaxies, the clearer it becomes. The beginning of everything was not slow, it was fierce. The cosmos did not take a gentle first step, it leapt, and that leap left artifacts, galaxies frozen in their premature brilliance, preserved in light that travels across eternity to reach us now. Every one of them a message that says, "You have not yet unlocked all the rules." There is comfort in that humility, because it means wonder will never run out. Our place in the universe is not to know everything, but to keep seeking, and these galaxies, the impossible ones, have become our greatest guides. They take our theories and give them edges, places where they fray, stretch, and ultimately break. And when a theory breaks, new knowledge grows in the space that opens. They are like lanterns lining a path we did not know existed. Perhaps the universe wants us to be curious. Perhaps curiosity is woven into the very fabric of reality. Because without curiosity, we would never have looked up. We would never have wondered. We would never have found the faintest glow of light still traveling to us from the dawn of time, a whisper that says, "Look closer." Every surprising galaxy keeps pulling us forward toward a new physics, a better understanding, a more complete story. A story where the universe's early speed is not a contradiction, but a clue. Where the Big Bang is not just an explosion, but the start of a process more intricate than we ever dared to believe. Where time is not a straight line, but a living, changing dimension. Where the laws of nature are not static, but still unfolding. Tonight, as you drift gently toward sleep, know this. We are explorers of a cosmos that continues to astonish itself. We are witnesses to truths still being written. We are made of the very stars that formed too soon, and yet right on time. You are part of a universe that learned quickly how to shine. And those distant galaxies, those improbable islands of brilliance, are reminders that even the smallest spark can illuminate everything when the moment arrives. They teach us that mystery is not what stands in the way of knowledge. Mystery is the path to knowledge. And so, as we continue deeper into ancient light, we embrace the possibility that the universe is not just older or younger than we think. It is wiser. It always has been. Now, with gratitude for the wonder we have uncovered, and for the mysteries still waiting in the dark, we gently turn the page. Let the impossible galaxies rest for a moment, their messages received, their contradictions cherished. And when you are ready, we will drift together into the quiet outro, a final reflection on the cosmic beauty we have explored tonight. Even now, as you rest here, the universe continues its silent expansion. Galaxies drift along the threads of the cosmic web. Stars burn softly in spiral arms. Light from the earliest moments of time keeps traveling, patient and unwavering, to reach our small corner of the cosmos. Tonight, we have wandered through impossible galaxies, systems that should not exist, structures that formed too fast, stars and shapes that outpaced every rule we thought was unbreakable. Yet, there they are, shining, real, waiting for us to understand. They remind us that the universe does not need our permission to surprise us. It builds in mystery, it evolves in wonder, it reveals itself only to those willing to look softly and with curiosity. As you breathe slowly, feel the comfort in knowing that not everything must make sense right away. Some truths arrive early, just like those ancient galaxies, and time helps us catch up. Your thoughts may drift now, gently loosened from the day. You are safe. You are small in the most beautiful way, part of a cosmos so vast that even its beginnings were filled with more creativity than we have yet imagined. Thank you for sharing this quiet journey through time, space, and possibility. If this exploration brought you even a moment of peace, I am deeply grateful you're here. Your gentle like, your soft tap on subscribe, and your kind presence mean more than you know. Now, let your mind settle into stillness. Let the stars keep their watch. Let sleep arrive slowly, like dawn rising over a silent horizon. The impossible universe is still out there, writing its secrets in light for you to one day discover again. Good night.